Hello, and welcome to this webinar. My name is Lucas Bayernis, and I'm a senior engineer at Dynaflow Research Group. Today, I'm going to present a comparison of the ISO 14692 and the ASME NM.2 codes with a specific focus on the key differences in the approaches to component design qualifications. Codes are extensive, and this is what we find to be the largest difference between the two. I'm going to be starting with the content, and afterwards I will be joined with by a colleague of mine, Edwin Schimmel, to go over a case study and answer some questions live. So for today, we're going to go some general remarks about GRP codes, a brief look at the philosophies in the GRP standards, and then we'll proceed to the comparison of the ISO 14692 and ASME NM.2 codes. So fiberglass pipe has been around for 50 years. It's a relatively new material and became popular in the 80s. So compared to steel piping codes, such as the ASME B31 code, fiberglass codes are a lot newer and differ slightly. So in general, a good piping code should be broadly applicable, and it should address the possible system and component failure mechanisms. So should also contain material tests for failure modes, so it's like axial and hoop shear failure. The load cases are very different than steel. Should define a different load case. So, for example, fiberglass cannot yield, so expansion load cases are not relevant. And of course, it should specify the limitations of the material properties and how they can be measured. So the strength, the max temperature, long-term behavior. And of course, a good code should specify how to arrive at a system that complies with these requirements. So how to avoid failure. So for example, that a pipe should not be in contact with hard objects, and should recommend on what analysis to perform and guidelines for those analyses. And a good GRP code covers a very large variety of products. So different processes of manufacturing, filament mount, hand layup, contact molded pipes and fittings, different resins, polyester, vinyl ester, epoxy, and all its curing agents, as well as it should cover all the possible loading conditions. So be it for above ground pipe, buried pipe, if it's pressurized, or if it's sewer pipe without any pressure. So what are the philosophies in GRP standards to do with design? So two basic philosophies. First is a base performance level. So this is to ensure through this process, you ensure that the product fulfills minimum requirements. So regardless of what the actual strength and material properties are, there's are values set for the minimum performance of material. And what this means is that if you have properties that are better than the minimum required, it does not benefit you in any way. So this also means that a GRP manufacturer, say in the context of a GRP code using base performance level, has no motivation to produce material above the minimum properties, just for the lowest possible cost. On the other hand, the performance-based design is based on the actual component properties. So instead of the minimum, so through testing, you can find out the actual strength of the material and make a design that is a lot more cost efficient and make it beneficial for a manufacturer to innovate and make a better product. So a bit of a visualization of what this means in this case. The red line could be considered the base performance level. So if the yellow dots are the true strength of all the products, this red line would encompass this base performance level. However, if you were to create a performance-based system design, perhaps you could draw the line closer to this point, or even let's say that this is across many manufacturers. Choose a manufacturer that is that encompasses, let's say, the points that we see at the very top of this graph. So some examples, the B31.3, as we said, is a code which has minimum performance level, and you have material specifications for minimum yield strength, tensile strength, all the allowables, flange pressure ratings. And it means that there's not much incentive to produce materials with better properties than the minimum required. On the other hand, ISO 14692, it's performance-based, and then the true properties are acquired through regression and qualification. Of course, that also means that it's different per manufacturer, and then the pipe stress calculations can only be made final when the pipe vendor and pipe type have been selected. Of course, when you have, let's say, material properties which vary greatly between manufacturers and there's no set standard, this often means that there is expensive qualification to be performed. So long-term tests are especially time-consuming and expensive. So regression testing is it's at least 10,000 hours for one of those data points, and it can be a very costly endeavor for a manufacturer, especially for, let's say, if we're talking about requalification for just an existing product. What this means sometimes is a caveat of this performance-based system design is that these qualification requirements are not always followed, and often justification of familiarity with the material or short-term testing justification can be used to let's say prove it for long-term use. So then let's take a look at a comparison of the ISO 14692 and ASME NM.2 for this perspective. So quick overview, ISO 14692, the first version came out in 2002, and it's a code that is performance-based system design, and it's applicable to onshore, offshore, buried piping, all sorts of fiberglass that are just not vessel. The ASME NM.2 encompasses the same scope as ISO 14692. However, the first version is only in 2018, so 16 years later, and it features both performance-based and minimum performance system design. And a bit of a difference from the ISO 14692 is that it is only applicable to piping with the design pressure of less than 17 bar, and the product of the pressure and the internal diameter must be less than 12.62 bars times meter. So as an example, a 16 bar pipe must then be less than 750 millimeters in diameter. Or let's say from the other way, if you have a DN 1200 pipe, then your design pressure must be less than 10.5 bar. So in the ISO 14692, you have this performance-based system design, and a very, let's say, broad overview of it is such. You perform one long-term regression test, so the ASTM D2992, to determine the long-term strength that consists of multiple internal pressure survival tests. And from this, you obtain the regression gradient and validate that with respect to the default gradient from the design code. That's done for one diameter of a straight pipe and applies to all diameters and fittings. So all of the same construction, so same epoxy, same hardener, same glass fibers. And then once you have this value, you get this long-term strength, this lower confidence limit, as it's called in the ISO. And you perform for each project, then let's say specifically 1,000 hour survival test, and that is to verify the long-term strength. So in theory, if your production process is very constant, you bake pipes, fittings in the same way. You determine the long-term strength of your pipes and fittings, and that applies, let's say, for all for the future. And then this strength is verified with 1,000 hour test. But then it is done for multiple diameters, for, let's say, representatives, and then for each component type, so pipe, fitting, flange, and for all joint types too. And from these qualified tests, you do a simple scaling formula. So basically, if I have qualified a DN300 elbow, I can then say that that's applicable to similar sizes around. And just a visual overview of this. So you do this one regression test, a survival test at our test, so at the non-biaxial loading ratio to determine an additional point of stress, perform a survival test, and then additional flange tests, as well as mass density, thermal expansion, and external pressure tests, or calculations to verify all the additional data required to analyze the system. And what that results in is the envelope that you see here. So basically, a survival test is done at this biaxial stress point, so this 2-to-1 loading. You also do one survival test at a non-biaxial loading point, so somewhere as a 1-to-1 ratio, and then you use an extrapolation down to the y-axis to determine this purely axial loading allowable. And from that, the compressive allowable is also determined, as well as the 0.5 here, the purely hoop allowable. It can be just taken from the survival test at the 2-to-1 loading ratio. So basically, 2 tests are required to verify this envelope. The survival test at the 2-to-1 ratio, so this is a pressure acting on an unrestrained pipe, as well as a survival test at R equals to R test. And this is an example of how this looks like. So this pressure in these 2 chambers is balanced to create the desired loading ratio between hoop and axial stresses. So one thing to note is that this, both the survival test at R equals to R test and 2-to-1 loading ratio, they're both considered long-term tests. Now, on the other hand, in the ASME NM.2, you must obtain 2 data points. So in the ISO, we saw 2 data points, so this 0.3 here and this 0.2. But in the ASME NM.2, you have to find the axial stress in the 2-to-1 loading ratio, so that is biaxial, as well as the axial stress in the purely axial loading mechanism, also loading state. Additional points may be used to develop a more complex allowable stress envelope, but that is considered optional. So basically, from these 2 points, from just these 2, you're allowed to determine your entire envelope. And the data points may become obtained from any combination of the methods. So method A, designed by rules; B, designed by long-term testing; C, designed by short-term testing; and D, designed by stress analysis. So for example, in this case, I can get the axial 2-to-1 allowable through design by rules, and then maybe the 0-to-1 allowable based on short-term testing, because that was available to me. And of course, the way that you arrive at that and the implications are very different. So the design by rules method A is one in which the ASME NM.2 prescribes allowable stresses for standard materials as listed in ASME NM 3.3. And these stresses are based on 1/8 of the laminate strength, so the short-term strength. And the pressure design of these components, when you design using these allowable stresses, must be then using the design by rules equations. So there's equations for sizing a straight pipe, which is straightforward, or elbow, or T based on the allowable stresses in each direction. And the material allowables have been determined for typical laminates. So you'll find, for example, the ASME NM.2 gives allowables for a filament wound vinyl ester pipe, and that's been obtained for a typical pipe for short-term burst testing, tensile tests, specimen tensile test, flexural tests, and so on. So effectively, this means that you have a factor of 8 from the short-term strength. On the other hand, design by rules is not allowed by ISO 14692. So the ISO 14692 strictly follows a performance-based system design philosophy, which means that allowable stresses are based on testing of actual components to be used in the system. In this case, with the ASME NM.3 allowable, that is for a typical laminate, and that is not necessarily the pipe that you will use, even made by the same manufacturer. So, of course, what that means, in the ISO, for comparison, the typical factor is 3.5 from short-term to long-term. So the D rating of a system-wide design part factor 0.67, some part factor of 3.85, and short-term to long-term, which is typically around 2. You get this 3.5. Let's say this is a very rough estimate of what you would typically see in a project. It can be a bit more. But of course, the key aspect here is that it is half that of the factor of 8 from short-term strength you see in ASME NM.2. So, yeah. Now, method B is designed by long-term testing. So this method is actually the most similar to what the ISO 14692 prescribes, and you use the same ASTM D2992 regression test to determine the hydrostatic design strength, and that's the say the lower confidence limit, the 95% confidence limit, times a service factor to get your design strength. And the design factor is chosen by the designer, but it must be less than 0.5 of the must be less than 0.5 of this long-term hydrostatic strength. And a bit of an indication, there's another requirement that the hydrostatic design strength must be less than a quarter of the short-term burst strength. So when doing long-term testing, this implicitly means that you must also do short-term testing, and that the factor must be 4 from the short-term strength, which of course matches the ISO. So if we say ISO is 3.5 to 4, this is very much in line with what you'd expect. However, what differs in this method B from the ISO is that the hydrostatic design strength is only used to obtain this biaxial stress point. And the ASME NM.2 does not recognize long-term testing methods to determine this purely axial data point. So as where we saw in ISO, there is this non-biaxial survival test that is not say considered in the ASME NM.2, and the long-term testing must be supplemented with another method. So either short-term testing or design by rules, or even design by stress analysis to get your envelope. What this also, however, what this means is that when you have this long-term testing and you've done this regression test to determine the hydrostatic design strength, you can use this equation to feed these design by rules calculations. So we saw in method A that it is required. In method B, it is not strictly required to use the design by rules equations, but if you do, you are not obligated to test your designed pipes, elbows, components in general, which of course means that your joint and workmanship quality is not checked, and the raw material selection is not checked. So how well does it bonding? What is the implication of choosing the materials you've done? So when opting to when chosen through this path, so even long-term testing, this does not mean that it is completely identical to the ISO, because you can, let's say, bypass any survival tests by just using the equations given in the code. Designed by short-term testing, right? So as we said, you cannot fully qualify a pipe in the ASME NM.2 through long-term testing only. And what you can do with short-term testing, well, is the full qualification. So short-term burst test to define this 2-to-1 biaxial loading point, and then the purely hoop and purely axial strength may be determined from either specimen tensile tests, so cutting a piece of the pipe and placing that in a test machine, or using, let's say, the entire pipe as a whole, so either an axial test on the pipe or a hoop tensile test on the pipe. The caveat from the long-term test, however, is that you have that the allowable stress must be less than a sixth of the short-term strength. So we said that in the long-term testing, we were allowed a quarter of the short-term strength. When you do short-term tests only, you're allowed 1/6 of the short-term strength. And of course, what that means is that because you cannot determine the 0-to-1, the purely axial tensile, the stress point with long-term testing, you must use this 1/6 factor, which is a very large difference from the ISO, which still would use the same 3.5 or 4 factor from short term. So yeah, in comparison, the ISO 14692 does not recognize any short-term tests. The concept of the code is to emphasize long-term performance. So you're designing a pipe for 20 years, a system for 20 years, and properties must be defined from long-term regression. And of course, it's obvious why, and that's because long-term failure mechanisms are very different from short-term failure mechanisms in GRP. And of course, to note, in the past, the ISO 14692 code did allow for the D2105 test. So as we see on the left column, same as the ASME NM.2 allows now. But now it's obtained using the 1,000-hour test. So previously there was some short-term testing in the ISO, but not anymore. Finally, you have this design by stress analysis method, and this is done by doing a biaxial stress analysis, so FEA, solving equations, or back calculation from strain gauges to determine the stress state at locations of concern. And using this method, the material properties may be obtained from testing or calculated purely theoretically. So it's possible that the pipe has never even been manufactured, or even individual lamina have not been created and tested, and still that can be used to determine the material properties. From this, say once the stress state has been calculated, a quadratic interaction criterion is used to determine whether the stress state is within permissible limits. And here the allowable stresses are either from tests of the actual pipe to be used, so short-term testing of the strain at failure, from which you would have to use a factor of 6 for your allowable, or you can use default strain limits, which then you would have to do a factor of 8. So, for example, in an oriented fiber, the ASME NM.2 recognizes 2% strain to be failure. So in this case, 0.25% strain would be the allowable. And of course, here we'll state that the ISO 14692 does not permit FEA for qualification. In general, there's very little written about FEA or recognition of FEA as a valuable method. And of course, sometimes there are geometries or complex, unique constructions that cannot be easily qualified or tested, and FEA does have some use in this context. So in general, more complex methods to evaluate stress are generally a positive addition, and writing that in the code or facilitating the qualification of these more unique components through FEA is a good thing. However, there are some limitations here, because what this means is that, one, it's in theory possible to qualify a pipe from purely theoretical values. So of course you end up with a factor of 8, but then the qualification is completely theoretical. The component has never been manufactured. But it's also more to the fact that analysis cannot reveal workmanship issues. So perhaps an uneven layup of T, or poor laminate bonding, the compatibility of the raw materials, and it also cannot expose manufacturing defects that are systematic. So perhaps there is a flange that has been designed, and the hub length is systematically too short, and that's not something that FEA would find, but that you would find with survival testing. Now, to some point, when the design by rules calculations are not used, in NM2, when using design method B and C, so the long-term and short-term testing, it is not required to do the design by rules sizing. And in that case, a proof of design testing must be performed. Now, for components of fittings, elbows, tees, there's one requirement, and that is to do a short-term hydrostatic strength test for 1 minute, so 4.5 times the design pressure for one component. It drops down to 3.75 times design pressure if there's 3+ components, as well as a long-term static pressure test over 168 hours, which is between 2.5 to 3 times the design pressure. Now, comparison, the ISO 14692 requires a survival test of 1,000 hours at around 2.75 times the design pressure at the default gradient. So we're talking about, in this case, an epoxy pipe with design temperature of 65 degrees. So typical case. And we see here that this requirement of 168 hours is exactly where we'd expect. So we find that this is was a pretty indicative of what the ISO does, and of course 168 hours is long term, so it falls on this regression gradient, typically considered more than 10 hours, and you've done a test now on a long-term failure mechanism, so we'd say this is quite consistent with the ISO requirements. On the other hand, so this is a special case in mandatory appendix 4. So for filament wound pipes, there are slightly different requirements, and that is that to do a burst test for 1 hour. So in the with the ASTM D1599 methodology, somewhat you set it up for a burst test at 4 times design pressure. However, in this case, failure is not required, so it's not meant to fail. It's just only supposed to pass at 4 times design pressure. And then only one component is tested and applicable to all diameters. So this, for one, the 4 times design pressure for 1 hour is a bit low compared to the ISO, depending on the gradient and whatnot. But the bigger aspect is that 1 hour is not a long-term failure mechanism. So with this test, there is no long-term failure that is being tested and not captured, and thus this would not be consistent with the ISO. So you're not the short-term and the long-term failure mechanisms are completely different, and with this test you are not verifying that sufficiently. Now, finally, of course, so we've talked about the qualifications as a final note. After qualification, what happens is a stress analysis of the entire system, and then following that testing on site. So the two codes in general, ASME NM2 and the ISO 14692, agree uh, pretty pretty well on this aspect. The consideration for load cases and the calculation of stresses is very similar. In general, codes do not have too much guidance on the how to perform a stress analysis, but in this case, the ASME NM2 is a bit more detailed with the requirements. One specific difference, though, however, it's significant, is that the ASME NM2 has highly detailed SIFs. So that previously was a feature of the ISO, but what we have is a hoop and axial SIF for both in-plane and out-of-plane moments. So that's 4 SIFs, a shear stress SIF due to torsion, and a pressure stress multiplier. So overall, that's 6 stress intensification factors. On the other hand, in the ISO, the SIFs are simplified. So the SIF is just 1.5, independent on the load direction, and it's applied on the adjacent pipe, so not the fitting. And that's based on some practical experience in that it is not the fitting usually that fails, but the pipe nearby. No pressure stress multiplier is used. And for the analysis itself, a load types, for the sustained load, a factor of 1 is used on the allowable. But the difference here is that in the ISO, when including temperature or the effective temperature, the factor goes up to 1.24, whereas it's only 1.1 in the ASME NM2. And of course, the ASME NM2 also differentiates between the length of the occasional load. So if it is 1 to 8 hours, it's 1.2 a factor. If it's less than 1 hour, if it's a hydrotest, then it's 1.33. And that's consistent with the ISO and the ASME. Finally, you have this idea of hydrotesting before putting a system online. And here the ASME NM2 and the ISO are very different in that in the ASME NM2, the minimum requirement is 1.33 times the design pressure for 10 minutes. And in the ISO, it is 1.5 times the design pressure for 2 to 4 hours, depending on if you perform this leak test. So in the you can see that the largest difference is both the time, so 10 minutes to 4 hours, as well as the design pressure, or the pressure to be used has to be 1.33. In the ISO, it is 1.5 times. In the ASME NM2, this means that the hydrostatics test is far from failure, and it's not robust to find the weak points of the system. In theory, you want a hydrotest to bring your system close to this, close to its allowable, so that you can find whether the design is fit for a 20-year lifetime. You have this higher pressure acting on the system, and you can identify now at the stage of commissioning whether there are any weak points, and with the procedure required by the ASME NM2, that is not sufficient. Additionally, failures the main concept is that failures take time to develop, and that 10 minutes pressure test is not enough to find long-term failure mechanisms, which is of course what you'd see in a system operating for 20 years. So in this case, the ISO 14692 is a lot more robust. And if you have a poorly designed system, you'd often see a failure, which is good for the long-term reliability of the system. So in summary, the ASME NM2 code is a bit is less battle tested in practice than the ISO 14692. So with the ISO 14692, there are already projects which had been developed using that code, which have reached the end of their project lifetimes, 20 years. So of course, there's a lot more evidence of reliability here than the ASME NM2, which is a lot newer. The largest difference between the two codes is that the ASME NM.2 allows for more diverse methods to qualify piping. And these diverse methods is that it allows to qualify piping without long-term testing. And of course, it's compensated by a higher factor. So typically 8 if there's no testing at all, or 6 with short-term testing from this short-term strength. And these multiple design methods mean that in theory, if you fail one test, you can just choose to go around a different design method. So if I fail a short-term test, I can go in FEA and prove that it will still work, even though I know in practice that it won't. On the other hand, the ISO 14692 only allows 1,000-hour tests to prove the strength of the strength of this material or the component. So there's no way around it. In every case, you must do it. And in general, well, so the guidance on the stress analysis is very similar, but where they differ is the hydrotest requirements, which I would find, in my opinion, the requirements in the ASME NM2 are a lot less robust. 1.33 times design pressure for 10 minutes is not as effective of a hydrotest as 1.5 times design pressure for 4 hours, because it cannot find the long-term failure mechanisms.